And so our next speaker is Airlie McCoy. She got her undergrad at the University of Adelaide in Australia. Then she got her PhD at the University of Melbourne. And then she moved here to the UK and joined Randy Reed's group to develop the phaser crystallographic software. And now she will give her presentation about solving your structure with molecular replacement at warp speed. So Airlie, please go ahead.
Thank you, Dorothy. It's good to see everybody here, and greetings to everybody on Zoom as well. I hope my videos work for you on Zoom as well. So I'd like to thank the organisers for inviting me. It's always a pleasure to be here. And I also thank Phil Evans. Oh, this is not actually showing my pause for some AV.
Okay, while we are waiting, we have more lost and found. Does someone miss a phone? Yeah, where did you find it? Just right here. So it seems to be a dangerous spot here. Yeah, so please, I have it here at the end of the session. If no one claims, and I will give it to Karen. Yeah, so please check your belongings.
Okay, apologies for the slight delay. As I was about to point to on the slide, there's also special thanks to Phil Evans for contributions through the pointless code. That the code is called pointless, not that the code is pointless, which is Phil's in-joke, not my in-joke. Right. So this session is about black boxes. So the black box I'm going to talk about is molecular replacement. So I'm going to start with an overview of the pipeline for molecular replacement, which is a process for solving the phase problem. And this is the approach post-2022, post-AlphaFold. So you start with your ligands and your protein sequences. And of course, the first thing you do now is look at your model. You might look at the domain structure of your model, and that will help you work out what sort of domain boundaries you need to be using for generating your crystals. You add your ligands, buffer and persistent, do your crystallization trials, and manage to grow your crystals. From there, you collect your data using all the wonderful new methods that we've got for collecting data, the synchrotrons these days. Then we go into the molecular replacement engine, the phasing by molecular replacement to get the phases, which then takes you into manual and automated model building, which combines the information that you have from post-translational modifications and sugars and so on, the buffers and precipitants to improve your crystal structure. You go through this cyclic process of refinement and validation. And then finally, when you're finished, you end up with deposition and analysis and writing your paper. Okay, so the black box, what's the black box? This session is about black boxes. What's the black box? There's the black box involved with the phasing by molecular replacement, that sort of phasing engine, which is what I'm going to concentrate on here. But more generally, we can talk about the black box of molecular replacement, which includes model generation and the protein sequences and that aspect of the process. But sometimes we just loosely use the term molecular replacement for the whole thing. So it's sort of a multi-purpose term. I'm going to concentrate on this core engine, and I'm going to talk about molecular replacement with a program called phaser. Now, I know people here come from many different backgrounds, and many people are coming into crystallography. So I'm going to introduce it. I've got a fantastic title from Dorothy, so I'm running with the theme of, there we go.
I'm a phaser.
What's a phaser?
Automated system. I don't have to be on fish.
You're using your own little sub-processes to build a smarter phaser.
Essentially correct. Phaser phrase. So the next step is today, you would require a model for this comparison.
Or knowledge.
You look. How to do parents. Proceed. Run program. Captain. Data has found something solution on any proteins which are non-glass. Because I survived the bed.
There you go. Okay, so yes, our survival depends on finding new protein structures. So why do we like phaser? So phaser is novel. That's the novel part of it. Is well, it was when it first came out. Is it uses maximum likelihood compared to Patterson methods, which are used by other molecular replacement programs. And the reason why we like maximum likelihood is that we get increased signal by accounting for the errors, and we also have powerful statistics underlying it, which gives us ways of predicting and judging solutions. So phaser in itself is sort of a pipeline in its own way. It has modules in it that does things called rotation functions, translation functions, packing functions, refinement modules, and it has a basic pathway through chaining different components together, where the first component is a different search strategy compared to the second and subsequent components, and it's able to do that sort of cycling in a limited kind of way. But the set of parameters that it uses at the start are fixed for any particular pipeline that you set up. So what makes molecular replacement difficult? Well, really bad data, metadata. Really bad models. Okay, so when you have bad models, you can divide your models up into smaller and smaller fragments, including secondary structure, little clusters, for example, as used by Archambault or Schroeder. If you've got that sort of a problem, collecting higher resolution data really, really helps. And of course, you can always use experimental phasing. Coiled coils are a particularly difficult case, different category of class, category of problem associated with those because they're very long and extended structures. The see above, you can use the small fragments and better data and experimental phasing for those. But there are also specialized tools developed specifically for use with coiled coils. And then finally, we've got the large search space with many, many parameters, which also feeds back into these other problems, of having bad models and so on. But this is the class of category that I'm basically addressing in this talk. So what's the problem? When you have many parameters, well, in molecular replacement with difficult problems, you have many parameters that can't be optimized in advance of molecular replacement. And when you optimize them, that's when you're going to get the highest signal and you're going to be able to solve your structure more easily. And these are discovered as part of the crystallographic experiment. So phaser needs to be run multiple times, exploring each category of uncertainty as it pertains to each particular problem. And of course, there are combinations of these uncertainties as well. So you get combinatorial explosion. And at least 7 categories of, I'm going to talk about 7 categories of uncertainties, basically, that I consider to be important as part of this process. And the aim, of course, is to make this simple. Ducks have a long history in crystallography. Of course, we're going to make this more modern. This goes back to Lyndon Johnson, 1976. We're going to use rubber ducks instead, the modern equivalent. You think the internet is full of cats? I can tell you it's not full of cats. It's full of pictures of rubber ducks that come in every possible shape and form. So, number 1, the accuracy of the error estimation. So you have an estimation of the errors of your models, which is normally expressed in terms of an RMSD, say 0.4, 1.2. But this is actually an uncertainty in itself. You don't know what value to put in. And this feeds through into molecular replacement, both in its ability to generate the right result, but it's also involved in the pathway through the process because it's involved in the calculation of something called the expected LLG, which changes the pathway. You also don't know how to divide your structure up or accumulate your oligomers or look at your domain divisions of your structure before you start. So these are all ways that you might model your biological unit, as we call it, and you would need to be searching over these different combinations of representations of your biological unit at the same time. There's also the problem of dealing with your search order permutations. So it's common in crystallography to find one component, for example, where B factor is very high. It's not scattering as strongly as you would expect it to. This structure sort of acts as a block to the molecular replacement. If you use a search strategy where you're looking for this one first, it will produce a very low signal, and then it will be very difficult to find second and subsequent components. So search strategies, searching strong scatterers to weaker scatterers is optimal. There's also the problem of the number of copies in the asymmetric unit. So when you have low numbers in the asymmetric unit, then 1 or 2, that's fine. You can just search over those quite simply. But it's when you have multiple copies in the asymmetric unit, there's not only the problem of having a large number, there's also the problem of having the uncertainty in that number as you're trying to generate your search strategies. And unfortunately, there's no way of knowing in advance what number is going to be the right number. You can get some ideas from, for example, rotation, self-rotation functions. Of course, if you've solved it before, you'll know, but coming in de novo, you won't know that. And unfortunately, you just have to try searching for n+1. So there's always this extra search at the end of every molecular placement process where you try to place that final component that isn't there. And then there's also the copy number search strategy. So if you have a lot of copies in the asymmetric unit, the most rigorous approach you can take is to take each assumption in turn. So you search for 12, you assume there are 12 in the asymmetric unit, you fix the total scattering as 12, which is an important component in the search, and then you search sequentially for 12, then you change your search to 13, and you search sequentially for 13, and so on, which is very time consuming when you have a lot in the asymmetric unit. If you are getting a good signal with by searching sequentially, so this is looking for the 8th in 8, and then the 9th in 9, and then the 10th in 10 as you're going along, sometimes that search strategy will work even though it's suboptimal, but it's a lot faster. So these are 2 ways of looking at your copy number searches, which I'm calling our fixed and dynamic search strategy for the asymmetric unit components. Then there's the issue of translational non-crystallographic symmetry. So this is a special case of the way that the components are distributed within the asymmetric unit, where the molecules are related by a translation, and this causes systematic intensity modulations. And if these are not corrected for, then the molecular placement problem becomes much more difficult. And one of the aspects of phasor is that it is able to do these corrections for the translational non-crystallographic symmetry intensity modulations. This symmetry is never exact. There's always differences in the sort of the mean vector and the angular perturbations between these components, and these need to be modeled and corrected for specifically. It is a significant aspect of the correction that these differences are modeled. And how do you know that you've got TNCS? Well, you can look in the Patterson, and the Patterson is something that you calculate just from the unphased data, from the intensity, so you don't need phasors to do this. So you can see in advance that you have this translational non-crystallographic symmetry, and that's how you start modeling it as part of your phasing strategy. But it's not quite that simple, because when you see these Patterson peaks, they usually can be interpreted in different ways. So for example, if you've got these 4 dots lined up, the simplest interpretation is that they're vectors of length 1/4, 2/4, 3/4, and so on, that you will see in your Patterson. But if you've got these rotational differences between them, it might be that you have a dimer separated by this 2/4 vector, and you need to be searching for these separately as another possibility for the interpretation of these vectors, where the breakdown between being translational, non-crystallographic symmetry, and just general symmetry is quite case dependent and case specific. So there's that problem of it. There's also the problem that when you see these vectors in the Patterson, they may not be associated with translational non-crystallographic symmetry. They could also be associated with something called lattice translocation disorders, where you sort of get shifts in unit cell dimension, unit cells next neighboring each other in the crystal. So you get some interference going on between these shifts, and you start to see these peaks in the Patterson. So even if you see a peak in the Patterson, sometimes it's not involved with TNCS. And then you've also got the problem of twinning and overmerging of the data. And sometimes you will have assumed that the crystal is one space group, and it isn't really. It's in a lower symmetry space group. So that's a very brief run through of all the problems that can make and what would otherwise be a basically simple molecular replacement system much more complicated. So we have loops over things like the alternative compositions of the biological unit, the number in the asymmetric unit, the dynamic or fixed total scattering, the permutations of the biological components, accuracy of the error estimation, interpretation of non-origin Patterson peaks, and space group translational ambiguities and subgroups, okay, all of these groups. Phase is not able to handle that level of complexity. It's basically a program that operates to produce solutions. So it's based around software that generates a file with a list of solutions. We've reconfigured phaser to phaser TNG, next generation, which these solutions know their relationship to each other. So it's much more focused on the solution. The information in the solution configures the software for each step of the pathway. So you can track through these complicated pathways with the solutions, knowing where they are, where they've come from, where they're going to as part of the pathway. And so you get these search trees of strategies as a result of phaser TNG. The search is customized for each problem automatically. And the pathway to the solution can be tracked through these directed asymmetric graphs or a tree of the search strategies. And this is just a visual representation of the simplest sort of trees that you get from the phaser TNG through to the more complex strategies where you're exploring much more of this space. And this new software for doing these pathways we've called Picard, which brings us me to halfway through the talk and another episode for you to enjoy.
Wouldn't that increase the output of the substation concept to be an improved response time? The process of killing under the reaction?
Yes. Examples from this, that's all. But or not.
There we go. Right. Apologies. Right. So yes, the re-engineering phaser has given us this new code base, which we can do lots of things with, not just make Picard. It's also involved in other pipelines that we've written, including, I'll just list them here, Riker, which is involved in more manual optimization in difficult cases. We also have X-Tricorder, which is like X-Triage in Phenix for analyzing the data quality, but specifically as it's involved in molecular replacement. There's Changeling, which is highly optimized for looking at contaminants, but also can look for screening of AlphaFold components, for example, to see which one is going to be more likely to give you a solution. And then there's Scotty, which is a way of beaming coordinates straight from the PDB, but also if you already know a structure, just doing wide angle molecular, wide search, local search, molecular replacement into your new data set. For example, if you've got a ligand problem. So this was tested in two ways. The first way was using the AlphaFold database that was developed by Tom Twilliger based on SAD, we call the SAD 215 dataset. It's took all unique SAD phase structures in the PDB in the 6 months between the 8th of December 21 and 29th of June 22. So this was before, after AlphaFold, after the cutoff date for the training of AlphaFold. And the assumption is that these could not be solved by molecular replacement. And as I say, there were 215 of these data sets. So we took the data from the original paper, which was solved with phaser, and compared it with the results from running Picard. And this involves doing molecular replacement, then rebuilding with Phenix auto build, and then using correlation coefficients to look at the results that are coming out of the pipelines and the results in the PDB. So on the left with phaser, this is the results from the original paper, just redrawn. And the thing to, and then on the right is the results from phasor T and G. And there are two things to note from this. The first is that there's better failure. So in other words, phasor T and G is giving you, telling you more when things go wrong. And it's also moving things across to the right, so getting higher correlation coefficients. This is, it's placing more components and more components more accurately, which is allowing the auto build to continue on. There were also 5 cases where phasor T and G was giving results where phasor wasn't. And then the next set of data is slightly more difficult. So that just was basically, if you like, vanilla molecular replacement, but it wasn't testing the part of the Picard script that is involved in pseudosymmetry. So this is exploration of space groups and subgroups. So we have to generate that data. It's assuming that all the data in the PDB doesn't have this problem of being in the wrong space group history. So we looked at the data sets that were overmerged, that could be overmerged, and overmerged them artificially. And this was new code written by Phil Evans in Pointless, as I mentioned at the beginning. And we had 144 data sets in this test set. So to make this clear, this is the data that can be overmerged, but we're assuming that the coordinates and the data in the PDB is correct in the subgroup. So it's not in the higher symmetry, it's not really in the higher symmetry. So when this was run, we did indeed get all the deposited PDB space groups back out of the pipeline again, except for one, which is kind of interesting. So in this case, the PDB deposit structure was in P21. It had twinning and 12 in the asymmetric unit, and it could be overmerged from P21 into P6322. And this is the complete set of subgroups that need to be explored in this case, because it's such a high symmetry space group. There are many subgroups, and just you can see the graphic of the pipeline that was reported by Picard at the end of the process. And this is the PDB redo output, just to compare the two structures. So you can see we've gone from P21 to P63, from 12 in the asymmetric unit to 4 in the asymmetric unit. The data here is reported without it being twinned. The R factor is lower and so on. So I'm not going to say these are better. I'll leave it to your judgment. You maybe want to vote on it at the end. So they're all given as question marks about what is being shown here. So, okay, we can deal with all of those. That's looking really good. Look, give me some more, make it harder. What harder structures? Right, so pseudosymmetries are the hardest sort of crystallographic problems. This I'm talking about the hardest. The structures themselves might not be particularly difficult or interesting even, but the problem arises specifically from the nature of the crystallographic problem. And those crystallographic problems are the hardest when there are pseudosymmetries involved in the crystal lattice. And this is a slide inspired by a similar slide by Andrei Lebedev's slides on Zanuda, except this one's involving ducks. So we have to start with, you see the laser pointer? Well, we can see this. So here we have just a normal crystal with no non-crystallographic symmetry. This is the unit cell translation here, and there's twofold here and two. These are the two folds in the crystal lattice. When you have general non-crystallographic symmetry, for example here, it's non-crystallographic, so these dimers are not lining up with each other. It doesn't propagate through the whole crystal. We've just got a dimer with a twofold in the asymmetric unit. And then when you have twinning, for example, around a twin axis here, you can see that you get these symmetries set up within the supercrystal with the extra twin. And this is where you end up with extra symmetries imposed on the diffraction pattern, but not truly present in the crystal. Okay, so then we get a little more complicated. When we have a pseudosymmetry that is parallel, almost parallel to a crystallographic symmetry here, simply we have a larger unit cell, then we start to get these crystallographic translations that I was talking about being set up within the crystal lattice. And then you can end up, when you're doing molecular replacement, with these sort of false structures where you have, it's a bit subtle here to see, but these have got a bigger space at the tail and a bigger space at the top here. But these are mixed structures, if you like, as part of the molecular replacement. And then you've also got twinning on top of that as well. So things can get really complicated with these twins. TNCS, pseudosymmetries, pseudocentering problems. So I'm going to generate some of these problems or find some of these problems in the PDB. These are using TNCS data that was found in a study by Airlie McCoy, who was interested in looking at the TNCS distribution within the PDB. We had 439 test data sets, and this just gives you an idea of the number of copies in 5 minutes. Okay, it's going to be fast. Okay, so we did a very similar analysis to before, and here we have a correlation coefficients of our true structures to our PDB deposited structures, and the ones in green, fantastic. What's going on here? We've got solutions that have got lower CCs. Is that Picard failing? Are those things that are wrong? Well, let's look at this in a different way. We're going to look at the amplitude correlation, the amplitude correlation of the top solutions to the deposited structure. And we see shifting from here, we end up with some structures that are high correlation coefficient in terms of Fs. And this corresponds to non-origin translations of the structure. So for example, here are the top 10 examples in that list. And you can see that we end up with a low map CC, but a high amplitude CC. Same space group, this is the TNCS, and this is the shift of a non-allowed unit cell translation here. There are a couple of interesting cases where it's also changed space group here and here. And that's another thing that happens when you have these pseudosymmetries and pseudocenterings. This is another slide inspired by Andrei Lebedev's slides. I won't go into it in any detail, but basically you have something like a C2 lattice and you drop different cell symmetries, and you end up with different subgroups of P21 or P2, depending on how these things are moving around. When you have it's the pseudo-centering that's giving you these options. Okay, so we can sort of explain these. What's going on here, where we have top solutions that are giving high CCs in, low map correlations, but higher F correlations, but not very high. Are these to do with twins, for example, where you've got partially correct solutions? So instead of looking at the top solution, let's look at any solution that comes out of phasor. So you phasor TNG, so you get multiple copies in some cases. That's the closest, and then we see that phasor is giving high correlation somewhere in the list. So these might be the other twin, for example. But there are still some interesting cases here. So this is looking at the map CC, and then this is looking at the F map. So these cases, it really doesn't want to give me any solution like something. It's similar to, but it's not identical to the one that's in the PDB. So what's happening with these two cases? So these two cases, again, looked at in PDB redo. So the first one, change in space group. Is this a better solution? Better R factors, better R freeze. That's an interesting case. What about the next one? So here we have the same space group, but it's in phasor TNG, doesn't require the twinning. We're getting a better R factor. Maybe that's a better solution. And then for these cases here, I was interested in looking at the top solutions where they were different from the PDB structure. Maybe there was something more interesting there as well. So this is another case where we have no twin required, significantly better R factors. Maybe this is a better solution. And again, we've got another change in space group and no twinning here with a better R factor. So these are interesting cases. So in summary, phasor TNG supports the development of multiple pipelines for phasing, most of which I have not talked about, including ones like for SAD phasing and EM docking. The particular script involved based on the phasor TNG code Picard supports a branching tree search for molecular replacement, optimizing search strategies over uncertainties. And it will be possible to go back to the theme of this meeting, which is AI. It will be possible to mine the results for optimal paths to structure solution to further optimize search strategies. And the summary of the summary is that you don't have to put any thought into the details of molecular replacement, which is a form of artificial intelligence, I would argue. And for that final episode for you.
or tending to employ alternate employee schemes. Possible combinations.
Oh. I don't know why that has failed, everybody. I shall go back and see what's going on there. Hang on. I apologize to people online. Is that it's a very dodgy system. So yeah. Well, I'm afraid I'm going to have to skip that in the interest of time. Oh. Oh, now it's all completely failed for me. So I just want to end with my acknowledgements to the Phoenix project, who we work very closely with, and happy to take questions.
Thank you very much, Airlie. Do we have questions?
Hi, Ellie. David Briggs, Francis Crick Institute.
Hello.
That was great. For the structures where Picard found the space group had changed, does Zanuda also suggest that something's up there, or was it just you needed Picard to show that?
Yeah, I haven't looked specifically with Zanuda, but these problems have been chosen specifically to have TNCS, which is normally a central symmetry operation with twinning and so on. So it's completely unsurprising that these are the sort of issues that will occur. Yeah.
We have a couple of questions on Slack.
Oh, sure.
The first one is, what will be the best strategy for coiled coils?
What would be the
Best strategy for coiled coils?
To use artificial coil or a program that's specifically designed for dealing with coil coils. Yeah, so the underlying process of phasor that uses the problem with using a whole model with a coil is that it's very long and extended, and this makes the search strategies particularly difficult, the search space particularly difficult. Yeah, the high resolution data really helps, and then yeah, a specific program for dealing with coils.
Now we have a second question about whether GPU can be used with phasor, TNG, or phasor.
No, it's no. Sorry, but multiple, yes, so it's threaded on multiple CPUs. Yeah.
Any other questions in the audience here in the room?